So we've got a crate on wheels here, so there's no friction, but it's got three different forces on it. One that's pulling to the left with 20 newtons, one that's pulling to the right with 50 newtons, another is pulling up and to the right with 40 newtons. I didn't draw that very well, and this is inclined at an angle of 30 degrees from the horizontal. And we want to know how much work is done by each force, what is the net work done, what is the change in the kinetic energy of the crate, and what is the final velocity of the crate. So let's get started. Now you should use given, find, and solve. And I'll just do it over here off to the side here. You should use given, find, and solve. But I've already drawn the picture, so this shows everything that's given. And so what are we trying to find? I'll put that down here. So we're trying to find, well, we want to know how much work is done by each force. Work done by each force. The net work done. And the change in kinetic energy. And finally, the final velocity of the crate. And I think I'll solve it over here. There's plenty of room up here. Well, we know that work is force times displacement times the cosine of the angle between them. So let's figure out how much work is done by the first force. I'll call that W1. And that's equal to F1 times delta x times the cosine of the angle between the force and the displacement vectors. Well, what is F1? It's 20 newtons. Now notice I just put 20 newtons. I don't put negative 20 newtons. You just put how big the force is, regardless of direction. It's 20 newtons. The displacement is 10 meters. But what is the angle? You need the cosine of the angle. And what is the angle between this force and this displacement? Well, they're in opposite directions. What's the angle? 180 degrees. I have to squeeze it in there. So W1 is equal to 20 times 10 is 200. A Newton times a meter is a joule. It's a capital J. And what's the cosine of 180 degrees? -1. So that puts a negative there. And there's my answer for the first force. Now what does negative work mean? Negative work means the force is trying to take mechanical energy away from my object. See, my object, now these guys, F2 and F3, they're going to add mechanical energy. F1 is trying to take that mechanical energy away. So that's what negative work means. It's trying to extract or take away or prevent it from gaining mechanical energy. Or energy. Okay, so for part B, W2 is equal to F2, which is 50 newtons, times delta x, which is 10 meters, times the cosine of, and look, F2 is to the right, the displacement's to the right, the angle between those vectors is 0 degrees. So that's just going to be 500 joules. And then for part C, oh wait, I'm sorry. That's not B and C. That's just part A still. Sorry about that. So W3, now this one's a little more interesting. This is 40 newtons. So again, it's how big this force is, how big the displacement is, 10 meters, times the cosine of the angle between. Well, the displacement is to the right. The force is 30 degrees up from that. So the angle between the two vectors is 30 degrees. And when you do the math, you get 346 joules. Okay, now we can do part B. And my pencil broke. Oh, there it is. Okay. So we want the net work done. Now, the way you think about the net work is two ways. There's two ways of thinking about it. It's the work done by the net force. So you can try to figure out what the net force is by adding these together as vectors and then dotting that with the displacement vector, but that's really hard to do. Just add up the work. You'll get the same answer. Just add up the work done by all the forces. So this is going to be equal to negative 200 joules plus 500 joules plus 346 joules. And when you do the net work done on that 50 kilogram cart by these three forces is 646 joules. Now part C, it says, what's the change in kinetic energy? Well, the work done by the net force, or the net work done, the work done by all the forces added together, is equal to the change in kinetic energy on the object. So that's just going to be 646 joules. And then part D. Well, we want the final velocity. And look, the initial velocity of the cart is given to be 0. So if I look at delta K is equal to K final minus K initial, well, the initial kinetic energy is 0 because the object starts at rest. So the change in kinetic energy is just my final kinetic energy. This is going to be equal to 1/2 mv squared. And there's my final velocity. So let's solve for it. The final velocity is going to be 2 times delta K divided by the mass. And then you have to take the square root. So I just did all the algebra in one step because I can do that. So that's 2 times 646 joules divided by 50 kilograms. And when you do that arithmetic, you get your final velocity of 5.08 meters per second. And there's our answer. Okay, so let's zoom all the way out. There we are. So here's the whole problem. Okay. So very similar to the kind of problem you'll get on a quiz or a test here, very similar. Any questions on this? Okay. That is all.